We saw that a second-order differential equation can be converted into a 2x2 system of first-order differential equations. Similarly, we can convert a 2x2 system of differential equations with constant coefficients of the form x prime equals ax plus by and y prime equals cx plus dy into a second-order differential equation with constant coefficients. Since we know how to solve such second-order differential equations, this will give us a method to solve these systems of differential equations. It's important to note that while this does give us a method to solve systems of equations, it will not be our main method for solving them. Our main method to solve such systems will involve the use of matrices, and is preferable because it will give us a better graphical understanding of solutions and will extend more efficiently to higher dimensional systems than a 2x2 system like this. To see this conversion, consider the 2x2 system of differential equations x prime equals ax plus by and y prime equals cx plus dy. To convert this to a second-order differential equation of y, we can compute the derivative of both sides of the second equation to get y double prime. In particular, computing the derivative on both sides gives that y double prime equals c times x prime plus d times y prime. Now, to get this completely in terms of y, we don't want to have x prime involved in our differential equation. Replacing x prime equal to ax plus by from the first equation in this equation for y double prime gives that y double prime equals c times x prime plus d times y prime as c times ax plus by plus d times y prime. Distributing the constant c gives ca times x plus cb times y plus d times y prime. But still, this equation has x involved. But notice, the term ca times x we can write as a times cx, where cx is equal to y prime minus dy from the second equation. So we can replace cx with y prime minus dy to get a times y prime minus dy plus cb times y plus d times y prime. Now our second-order differential equation is completely in terms of y. But we can clean it up a bit from here. Distributing the a gives a times y prime minus ad times y plus cb times y plus d times y prime. Collecting our terms with y prime and our terms with y, we can write this as a plus d times y prime plus bc minus ad times y. And we now have our 2x2 system written as a second-order differential equation for y. And we can write this second-order differential equation in our standard form by moving all terms to one side to get y double prime minus a plus d times y prime plus ad minus bc times y equals 0. And as a second-order differential equation, we can solve this for y of t. And once y of t is known, we can solve for x using that c times x is equal to y prime minus d times y. Although I should note that if c is equal to 0, then you cannot solve the above equation for x, and will need to solve for x in the first equation as a first-order linear differential equation. Whichever way we solve for x, this will give us both solutions, x of t and y of t, in the system. In other words, the solution to our system of differential equations.